Hi, I'm Rogério Esposito, one of the authors of this book, and today we're going to talk more about the power and some applications of this important tool for reservoir engineering. Come on, let's go. Well, one of the most important applications of compositional grading is to predict the fluid composition at any point of the reservoir from only a few selected samples taken at some reference points. Samples are very expensive, right? And if you are able to use the information of the experimental data coming from them, you save a lot of money on calculating composition, pressure, and thermodynamic properties elsewhere. Compositional grading also helps detecting barriers, interfaces, fillings, or liquids in the reservoir. It's a very important characteristic because if you assume some premises and results doesn't match the experimental data that you observe, something else is going on. And you must answer which thing is that. Okay, if we're able to calculate the composition all along the reservoir, this settles a representative compositional distribution to be used on the initialization of the reservoir simulator. And this also increases the reliability of the production forecasts, or the very important characteristics, right? Well, after all, compositional grading validates the thermodynamic model, generally an equation of state, which is fitted on PVT data. Well, let's see uh, a little bit of the equations that compose the modeling of this problem, right? If you assume that the reservoir is isothermal, and we have already talked about that, right? You have to solve the so-called gravity-modified Fugacid equations, right? But if you assume that the reservoir has a thermal gradient along depth, for example, a 1D thermal gradient, then you have to solve the diffusion flux equations. But in the general case, if you have a thermal gradient all along the reservoir in the three directions, you have to solve the general flow equations of reservoir engineering, right? Well, can you prove that this third equation right here will collapse to the flux, to the diffusion flux equal to 0 of the 1D non-isothermal case if you are on steady state? This is very important too. Okay? Moving on, it's also possible to demonstrate that in the absence of a thermal gradient, in isothermal systems, the expression of the total diffusion flux collapses to the gravity-modified fugacity equality, right? You should start from this equation here, and you should reach this one. We did it in the book. Check it out. It's very interesting. And finally, this is a real case study, which is also very interesting. Right? It is about a system under filling. And this graph is about the methane mole fraction variation along depth. You can see that above 5,300 meters, right? The experimental data start deviating from our calculations for both isothermal and non-isothermal systems. So something's going on there. And what's going on? Well, there is some gas getting in the reservoir, methane-rich gas getting in the reservoir. And how can we obtain the rate of gas filling from this information? Is the graph compatible with the observed GOR? It must be, because GOR should increase with methane molar fraction increase too. And finally, where's the gas getting in by? Under an aerial perspective, right? You have only the depth information. But where exactly is the point at the whole reservoir in which gas is getting in by? This is also very important. Okay, if you want to know more about compositional grading, please get the book. Take a read it. I'll be happy to answer your questions. See you. Thanks.